Good morning. My name is Richard Thill, and thank you for attending my thesis presentation titled The Installation of a Hydrogen Bubble Flow Visualization Apparatus in the Webb Flow Channel. I'd like to begin this presentation with some acknowledgments. First, to my principal advisor, Professor Royce, for his continual guidance and practical mindset. Because it is your birthday today, I left you a bottle of Diet Coke in the back of the auditorium. I would like to also thank my readers, Professors Onis and McMahon, for their assistance with my thesis and associated writing, as well as my editor, Professor Harris, for his grammatical and stylistic edits. I'd like to also thank Professor Martin for his assistance with electronics and overwhelming optimism, as well as Pat Doherty and Jamie Swan for their assistance in the Haberly Lab and Machine Shop. I'd also like to thank Dr. Scott Black of the Webb class of 1990 for providing reference information. And lastly, Will Calley and Miguel Sanchez for allowing me to test my apparatus with theirs, and Alex DeMayo, Matt Coogan, and Darren Cook for assisting with taking pictures and videos during my testing. The outline for this presentation includes a statement of the objectives for my thesis, background and associated theory, as well as apparatus design and construction, testing and results, conclusions drawn from the results of this testing, and lastly, recommendations for future work. The objectives for this thesis were to design, manufacture, install, and test an apparatus in the Webb Flow Channel that allowed for the use of the hydrogen bubble flow visualization method. I also wanted to compare the performance of several different types of wires and create a user manual to ensure the safe and efficient use of the apparatus. Lastly, I sought to elaborate on the hydrogen bubble flow visualization method and introduce the flow channel into the Webb curriculum. Flow visualization's main purpose is to make flow processes visual for qualitative or quantitative analysis. It is often used to visualize vortices, eddies, von Karman vortex streets, and boundary layer effects. An example of a von Karman vortex street can be seen to the right. History regarding flow visualization includes its first documented user, Osborne Reynolds, in his 1883 flow criticality experiment, where he sought to determine the transition point of flow between the laminar to turbulent regime. There are three methods for flow visualization, the first being the marked boundary. An example can be seen here where India ink is used to visualize Raleigh-Taylor instabilities. There are also refractive index methods, a common one being the Schlieren method, seen here visualizing the shock wave produced from a bullet. And lastly, particle tracking techniques, where particles are introduced into flow to highlight path lines around geometry. An example can be seen here with a Cybertruck. The hydrogen bubble flow visualization method is an example of a particle tracking technique. The general principle upon which the method relies is the production of hydrogen bubble sheets via electrolysis. This is detailed further later. These bubble sheets are then entrained into the surrounding flow and used to visualize that flow over a submerged downstream geometry, as seen to the right. There are certain advantages with this method, including no introduction of foreign particles, which helps keep the properties of water in the flow channel consistent. There's also minimal added flow disturbance, helping preserve natural flow processes. And also, the time pulsing of bubble sheets is allowed, which allows the user to track changes in those bubble sheets down the length of a test section, as seen in the video to the right. There are some disadvantages with the method, namely that it is particularly sensitive, both to particulates in the flow channel and user error because of the very fine wire often used. An example of a typical wire can be seen to the right versus an average human hair. It is also potentially expensive as platinum is often used, which costs about $130 for a 5-meter spool. There was little to no internal previous work for my thesis, so I had to rely on external sources. This included Collins in 1953, who was the first to use the method, where he visualized parabolic velocity distributions inside of a pipe. Geller in 1955 was the first to use a 0.025 millimeter diameter platinum wire, and the David Taylor Model Basin in their 1966 experiments, whose work my thesis was mostly based off of, was the most comprehensive. They provided an initial drag and buoyancy analysis and discussed intricacies and problems associated with the method. Fernandez and others, in a more recent work, utilized chemistry to explain some of the problems that the David Taylor model basin faced. To go into a bit more theory, specifically regarding electrolysis, it is defined as the chemical decomposition produced by passing an electric current through a liquid or solution containing ions. In this example, a platinum cathode and stainless steel anode are used. The application of direct current or DC power and an induced electrical current is supplied from a DC power supply. The result is the production of gaseous hydrogen and oxygen. The driving equations upon which this process rely are the hydrogen evolution reaction, or HER, which occurs at the surface of the cathode. Here, water molecules and electrons delivered by DC voltage combine to form hydroxyl ions and gaseous hydrogen, used to visualize flow. At the surface of the anode, the oxygen reduction reaction, or the ORR, occurs. Here, hydroxyl ions are recombined into gaseous oxygen, water, and excess electrons driven away by the DC voltage. Lastly, Ohm's law helps to relate the applied DC voltage VDC to the induced DC current IDC through the equivalent resistance of the system, REQ. Now that I understood how electrolysis generates hydrogen bubbles used for flow visualization, I began to examine variables that may affect my apparatus design. This included a further analysis into the equivalent electrical circuit, which helped me determine my DC voltage requirement. I utilized the Nernst equation, pictured above, which is a thermodynamic formula meant to express chemical reactions in terms of a necessary voltage. By substitution of the HER and ORR as previously shown, the two following formulas are produced. They relate the necessary applied voltage to the pH or acidity of the electrolyte. By plotting these two formulas over a range of pHs from 0 to 12, and producing the figure to the right, where voltage is on the y-axis and pH on the x, and selecting 7.5, which represents the acidity of standard tap water, it was seen that the applied voltage requirement is only 0.443 volts, which any DC power supply should be able to produce. Further analysis of the equivalent electrical circuit helped refine the required capacity of the DC power supply. My analysis was focused on the cathode side, as only secondary reactions occur at the anode. There are several components to the equivalent resistance of the system, REQ, including a capacitance due to the cathode material, a resistance due to a layer of concentrated hydroxyl ions, and the resistance of the electrolyte, or in this case, the water. Due to the presence of the capacitance in the circuit, the relationship between induced DC current and applied DC voltage may have been affected, especially when the bubble sheet pulsing was incorporated. In summary, though, I determined the theoretical voltage requirement and learned that the relationship may not be linear. Further testing was carried out and is detailed later. I then moved on to a drag and buoyancy analysis. This sought to answer the question, won't the bubbles float too much? I utilized a first principles analysis and a free body diagram to generate equations of motion in the x and y direction, which represent the direction along the flow channel and the vertical, respectively. By summing the forces in the x direction, which included the drag due to surrounding flow, the induced drag due to motion of the bubble, which summed to equal the mass of the hydrogen bubble plus its added mass, times the acceleration in the x direction. Similarly, summing the forces in the y direction produced the buoyant force, the weight of the hydrogen bubble, and the induced drag due to vertical motion. These once again summed to equal the mass of the bubble and its added mass, this time times the acceleration in the y direction. By solving and plotting these equations of motion, with the free stream velocity u varied between 0.152 and 1.52 meters per second, and other variables such as the bubble diameter kept constant, I was able to produce the plot on the right. It shows the vertical displacement of the bubble in millimeters on the y-axis and the longitudinal displacement of the bubble in meters on the x-axis. At a 3-meter length down the flow channel, which represents the length of the plexiglass test section, the vertical displacement of the bubble was expected to be 2.3 millimeters, or about the thickness of 2 pennies stacked on top of each other. Therefore, the bubbles are not expected to rise appreciably over the test section in the flow channel. In regards to my apparatus design, there were a few key requirements. This included that it had to be safe, provide enough power for the hydrogen bubble flow visualization method, allow for bubble sheet pulsing to take advantage of the benefits previously described, and lastly, incorporate a fixture that holds several lengths of wire in either a vertical or horizontal orientation, minimally disturbs flow so that natural processes are preserved, and is strong enough for use in the flow channel. For my DC power supply selection, the theoretical voltage requirement was only 0.443 volts, as previously stated. However, the expected current range was between 50 and 100 milliamps. Therefore, I selected a Kung-Bear DC power supply with a 120 volt and 3 amp capacity. The voltage capacity was oversized so that the expected current range could be induced, accounting for the total resistance of the system. Bubble pulsing was incorporated into my design through the use of an Arduino Uno and DC relay, as pictured to the right. These work by periodically breaking the circuit and preventing bubbles from being produced in a manner that the user can easily control. I also wanted the user to be able to control what wires were on in either the horizontal or vertical wire configuration. Therefore, I created an electrical box with 4 switches, as seen to the right. In regards to the fixture design, it boasts a vertical orientation where, in the figure to the right, the wires can be seen in red. Additionally, it has a horizontal orientation where the wires can once again be seen in red. It allows for the easy positioning and changing in the length of wires, and utilizes off-the-shelf items such as carbon fiber airfoil tubes meant to disturb the flow as least as possible, and 80/20 aluminum extrusions. Lastly, I relied on 3D printed connections for their versatility and low cost. I carried out initial testing in still water as a sort of proof of concept. As can be seen in the picture to the right, hydrogen bubbles were formed along the surface of the platinum wire, and similarly, oxygen bubbles on the stainless steel nut, supporting my theory. I then carried out testing to determine the relationship between applied DC voltage and induced DC current, and produced the figure shown to the right, where the measured amperage is on the y-axis and applied voltage on the x-axis. As expected, the relationship was linear, suggested by the high R² value. I then carried out the same testing for a platinum and copper wire and produced the plot seen to the right, with the same axes as before. The linear relationship was maintained for the copper as well, as the R² values were also high. Lastly, I investigated the effect of electrode separation distance on the equivalent resistance of the system, REQ, and produced the graph seen to the right, which shows REQ on the y-axis in ohms and the distance between electrodes in millimeters on the x-axis. As can be seen, REQ increased greatly with increasing electrode separation distance. This suggested it would become an important consideration in my final design. I then carried out more initial testing, but this time in the flow channel. I reinvestigated the effect of electrode separation distance and produced the graph seen to the right, which has the same axes as the one shown previously. As seen, the result did not trend the same way as the resistance approached a bulk value. This is because of diminishing percentage increases in the total volume of water in the circuit with further electrode separation because of an already large volume of water present when compared to my still water test. I then carried out testing with geometry downstream in the form of a broomstick handle, where I expected a von Karman vortex street to develop behind it. But, as seen in the video to the right, it was not easily visualized. This result suggested that there was a necessity for selective lighting, where a flashlight would be used to illuminate the bubble sheet while testing at night. The result from testing the same geometry, but at night, can be seen in the video to the right. The von Karman vortex street is easily seen. I then assembled my apparatus in its vertical wire configuration and installed it into the flow channel. I used the 0.025 millimeter diameter platinum wire, which is very tricky to install, broke often, and I once confused it with a strand of my own hair. However, a single bubble sheet can be seen being produced in the flow channel in the video to the right. I then used a submerged oscillating cylinder, generously provided by Will and Miguel, where I expected a von Karman vortex street to develop behind it. This first video shows the flow ahead of the cylinder, where the path lines are clearly highlighted by the bubble sheet. The second video shows the flow behind the cylinder, where the von Karman vortex streak is clearly visualized. I then carried out testing with 0.1 millimeter diameter nichrome or nickel chromium wire. It was a much larger wire, did not have as ideal of a wire chemistry, but was suggested for use in previous work, so I decided to test it as well. I carried out a pulsing demonstration where a single bubble sheet can be seen being pulsed on and off in the video to the right. I then used the same cylinder as before, and once again, this first video shows the flow ahead of the cylinder. The path lines are still highlighted by the bubble sheet, but admittedly, the sheet is a bit streakier than that produced by the platinum. However, by looking at the flow behind the cylinder, the von Karman vortex streak was visualized just as well. The apparatus was tested at a max flow speed of about 0.7 meters per second, demonstrating viability for use in the flow channel. Some conclusions regarding my thesis include that the apparatus was successfully designed, manufactured, installed, and tested, but the lighting turned out to be much more important than I had originally thought. The 0.1 millimeter diameter nichrome wire appeared ideal for use with my apparatus, as it's about 16 times stronger and 1/40th of the cost of the platinum wire, yet produces very comparable results. A user manual was written that details the design, installation, and usage of the apparatus, and theoretical questions were answered, specifically regarding chemistry and the drag and buoyancy analysis. Lastly, the utilization of the apparatus is to be monitored. I will keep a close eye on all Webb annual reports.
Great.
Some recommendations for future work include the development of a dedicated lighting system such that the apparatus can be used in a proper lab or research setting, as well as the integration of the particle image velocimetry or PIV system, so that qualitative as well as quantitative analyses of flow around submerged bodies can be conducted with my apparatus. Thank you for listening to my presentation. I would now like to invite Tim and Coda up to present their thesis. Please hold all questions until they and Jack Otto are finished.